Hello everyone. In this session, we will learn how to simulate single-phase full-wave inverter. Now, before going to simulation, we'll discuss few terms about an inverter. An inverter is a DC to AC power converter. In an inverter, we require switching devices. The switching devices are normally MOSFETs, IGBTs or MCDs. Now let us see the circuit diagram for an inverter. This is a circuit diagram for a full wave inverter. Here we can see there is the input applied is a DC voltage source. The switching devices used here are IGBTs and there is a load across which we will get the AC output voltage. Now in an inverter there are two cases. In the first case the IGBTs Q1 and Q2 are made on by triggering their gate terminals. At that time the IGBTs Q3 and Q4 are made off. In the second case, the exact opposite happens. That is, the IGBTs Q3 and Q4 are made on by triggering their gate pulses and IGBTs Q1 and Q2 are made off. Now let us see these both two cases. In the first case, the IGBTs Q1 and Q2 are made off and Q3 and Q4 are made off. The current flows from positive of the DC supply through the Q1 through the load Q2 and towards the negative of the power supply. Now in this way the voltage we acquire at the load is positive Vs. Now in the second case the Q1 and Q2 IGBTs are made off and IGBT Q3 and Q4 are made on. In this case the current flows from positive of the Vs through the Q3 load Q4 and towards the negative of the Vs. In this case, the current direction is exactly opposite of in the first case. In the first case, we can see the current direction is in this way, and in the second case, the current direction is in the opposite way. So, the output which we get in the second case is negative Vs. Now, in this way, we will get the waveforms. Let us observe the waveforms. Suppose these are the waveforms applied to the gate terminals of IGBTs Q1 and Q2. At that time, when the IGBTs Q1 and Q2 are made on, at that time the gate terminals of the Q3 and Q4 IGBTs are 0. And when these two are 0, these two are made on. In this case, we will apply the switching technique. The output which we observe is in this fashion. That is, in the first case, we will get the positive Vs, and in the second case, we will get the negative Vs. And this cycle continues. Now, let us simulate it using the PSIM platform. First, open the PSIM software. Now click on File and create a new file. On this page, we will have various components which are used for simulating it. Now let us select few components which are used here. First is the DC voltage source. The switching device we can use is MOSFET or IGBT. Now let us select the IGBTs here. We can use a load as a resistive load. Now the switching devices requires a pulse generating block. So we will apply those pulse generating blocks. Now let us connect the circuit using the wires. Now we will connect the load. Now connect the pulse generating blocks to the IGBTs. Now as I told earlier, the IGBT Q1 and Q2 are connected or may turn on during the same time. So we will connect the same pulse generating block for the IGBTs Q1 and Q2. And it is same for the IGBTs Q3 and Q4. Now we require a voltmeter to observe the voltage across the load. So in this way the circuit is connected. Now let us apply the input voltage is of 100 volt. Okay. The pulse generating block requires the frequency. So let us give it about 200 Hertz. Now as we have seen in the waveforms, there requires a phase delay in the for the IGBT is Q3 and Q4. So we will apply a 50% phase delay here. Now we require a simulation control box to run the simulation. Using this simulation control, we will decide the total time of the simulation. So let it be 50 milliseconds. Now save the simulation. Now run the simulation. Here we have not given the value of the resistive load. Let us be 10 ohms. Now we will run the simulation. So we can observe here that the input voltage we applied is a DC voltage and the output which you get is between plus 100 to minus 100. That is the plus Vs to minus Vs. Now let us observe the pulse generating blocks, the waveform at the pulse generating blocks using the voltage probes. First we will add the V1, that is the first pulse generating block, then screen, add screen, then the second, and finally we will add the voltage across the load. So we can see here, when this is 1 volt, the pulse rating at the Q3 and Q4 IGBTs is 0, and when it is off, it is on. And at the output we can see the AC voltage waveform. Now we can change the firing angle. So now it is the duty cycle is of 50%, that is 0 to 180. Now let it make as 0 to 90, and for it we will make from 180 to 270. Then the duty cycle is made of 25%. Now first we will add the V1. So we can see the duty cycle of 25%. V2. And finally the. So here we can see that when this is on, we will get a positive 100. And when it is on, we will get a negative 100. But there is some amount of time period in which the V1 and V2, that is the both the pulsating blocks are in off state. At that time, at the output, we will get a 0 voltage. So it is a discontinuous mode. Okay, to avoid it, we will have a 50% duty cycle. So when the duty cycle is 50%, there is no discontinuous mode. That is, there is no constant voltage as 0 volt at the output. Now here, using the measure, we have the various options. We can get the average value of the waveform as well as the RMS value. Now we will delete the unwanted screens. So now we will find the RMS value of this waveform. It is 100 volt. Now, how we can calculate the RMS value? We know that the formula Vout is equals to Vs into under root delta upon pi. Now here delta is the on time. Now if we add a screen, suppose let take it V1, the on time is from 0 to 180. That is the on time is 180 degree. That is the delta is 180 degree. And pi is also 180 degree. So the Vout is equals to Vs. So that the Vs is 100 volt. Thus the RMS value which we get is also 100 volt. Now if we change our duty cycle, suppose I will make it again 25%. Then we will have a different RMS value. For this case, major RMS value. So we can see that it is 70.71. As the delta is here is of 90 and pi is of 180, therefore Vout is equals to Vs into 90 upon 180, that is Vs upon root 2, that is 70.7 volt we get. We can also obtain the different waveforms by changing the load here. So this is how we will get the AC supply at the output using the switching devices and controlling their on-off period. Thank you.